Black holes. For decades, they perplexed the scientific community. A region of space time from which nothing, not even light, can escape? Such a concept seemed to come straight from a science fiction book. However, these extreme celestial bodies did not remain the subjects of a sci fi writer's imagination for long. In 1915, Einstein unveiled his general theory of relativity, which describes how mass bends spacetime, producing gravity. This theory paved the way to the realization that matter could be packed into an infinitely warped region of space. Then, in 1974, Stephen Hawking concluded that black holes are not completely black. Instead, they emit a faint haze of particles, known as Hawking radiation. As a result, he theorized that black holes should slowly evaporate until they explode. Most recently, in 2019, the first picture of a black hole was captured by a team of international astronomers. And although this picture serves to clear up several question marks surrounding our somewhat nebulous understanding of black holes, not all of their mysteries have been unraveled quite yet. Today, we are going to be talking about the black hole information paradox and why black holes could hypothetically delete the universe. Let's begin our story by defining information. Information is not tangible, rather, it's typically understood as a property of the arrangement of particles. Imagine you have a bunch of carbon atoms. Arrange them one way, and you get graphite. Arrange them in a different way, and you get a diamond. The atoms remain the same between these two objects. What changes is the quantum information of the particles, such as their position, velocity, and spin. Every object in the universe is composed of particles with unique quantum properties, and therefore unique information. Even if you destroy an object beyond recognition, its quantum information is never permanently deleted. For example, let's say you go camping and burn a log of wood. The ash that's left over from the fire will never become wood again, but theoretically, if you were to collect every single product of that reaction, including the ash, smoke, and heat, you would be able to reconstruct the log of wood. The quantum information of the wood is still in the universe. It's not lost, it's just hard to read. This idea is one of the principles upon which much of modern science is built. It can be summarized in the theory of quantum mechanics. The total amount of quantum information in the universe must be conserved. The problem arises, however, when we try to apply this concept to black holes. If we were to throw an object into a black hole, it would appear as though all of its quantum information is permanently lost. This does not immediately contradict the laws of physics, assuming the object's information is conserved either inside or on the surface of the black hole. That is, until we account for the Hawking radiation we mentioned before. This phenomenon shows that black holes are gradually losing mass as they shed particles away from their event horizons. Critically speaking, these radiation particles are independent of the material entering the black hole, meaning that the quantum information of the object sucked into a black hole would be permanently lost. Does that quantum information truly disappear? If not, where does it go? The black hole information paradox poses these and many other questions to physicists. And although that may seem unsettling, it is paradoxes like these that help reshape our understanding of the universe.